Hi there. Thanks very much for tuning into this session from the Faraday Institution Characterisation project. My name's Rob Weatherup from the University of Oxford, and I lead a project on probing buried interfaces in working batteries. And this is a collaboration across three main institutes. There's several of us at the University of Oxford, and we'll hear later from Josh Gibson, who's one of the postdoctoral researchers on this. And he collaborates also closely with Diamond Light Source, where Tianlin Li is the principal beamline scientist at IO9. And we also have a number of collaborators at the University of Manchester, and we'll be hearing from the postdoctoral researcher there, Zoe Henderson, about some of the work she's been doing, carrying on from earlier work started by Connor Byrne. So in this project, we're trying to develop new techniques for characterizing battery interfaces. But why are we so interested in battery interfaces? Well, this is where a lot of the action happens in energy storage materials at the electrode-electrolyte interface. We can think about our simple lithium-ion battery where we shuttle lithium back and forward between a transition metal oxide cathode and a graphitic anode. And various processes might occur. We might have transition metal dissolution from the cathode, the evolution of gases, and potentially the reconstruction of the surface of the cathode, as in the rock salt reconstruction formed on NMC materials. And this all occurs within a few nanometers of that surface, so we really need interfacial sensitivity to be able to probe what's going on. Similarly, at the anode, we might have electrolyte decomposition going on to form the solid electrolyte interface, and things such as lithium plating, where we form dendrites, etc. Again, all happening within a few nanometers of this surface. So how might we go about probing interfaces? Well, both electrons and ions give very good sub-nanometer surface sensitivity thanks to their short mean-free paths, and are used in techniques such as X-ray photoelectron spectroscopy and secondary ion mass spectrometry. But in both cases, measurements are usually restricted to vacuum. So if we think about our X-ray and XPS, this comes into the surface and probes deep into the bulk of the material, but we're only getting the surface sensitivity from the first few nanometers of this material because that's where the photoelectrons are able to escape. But if we then think about trying to do this with a liquid or solid electrolyte on top, that's going to block most of the photoelectrons trying to escape, making it very challenging to probe that interface with surface sensitivity. So the general approach is to perform ex situ measurements, where we would take apart our cathode, anode, separate them in a glove box and transfer them inertly to a measurement instrument or beamline. And here's an example where we've used hard X-ray XPS in order to depth resolve through the solid electrolyte interface formed on a graphite anode. And you can see here the carbon 1s spectra taken with soft X-rays, the green line, so-called SOX pairs, and with increasing X-ray energies. And what we see is with soft X-rays probing near the surface, we see a very weak graphitic signal and much more stronger contributions from carbon-hydrogen and carbon-oxygen bonds related to the SEI layer on top. But as we probe more deeply with higher energy X-rays, we see much more intense contributions from the graphitic peak. And from this, we're able to measure across a number of different cycles and get an idea of how the solid electrolyte interface layer is thickening with cycle number. So we see there's initially a very rapid thickening after only 10 cycles, and as we go to increasing cycle numbers, we see this more gradual thickening. And we can do the same for the cathode and look at the thickness of the cathode electrolyte interface that forms. And Eric Bjorklund has a poster on this, so I'll leave further details on that to him. So in this project, we want to move beyond this ex situ approach by developing a number of new tools. And we want these tools to work across a wide range of different measurement platforms. I already mentioned XPS and SIMS, but we might also want to use them in SEM, XRD, etc. And we want those capabilities to be relatively agnostic to chemistry, so we can look at various different battery chemistries, probe both solid and liquid electrolytes. And we want all of this to be compatible with existing infrastructure so that we can use these with existing glove box capabilities. And finally, and most importantly, these need to be electrochemically realistic. We want to understand what's going on in a real battery rather than coming up with some idealized system that isn't very representative of that. And so we take a multi-pronged approach to do this. I'm going to talk you through in the next slide how we use an in situ approach, and we distinguish an operanda approach, and finally a cryo-fixing approach in order to look at these buried interfaces. So in the in situ approach, this initially appears similar to what we might do with an ex situ measurement, where we measure our electrode under vacuum conditions in a measurement chamber. But then importantly, we're able to reassemble this battery under those inert conditions, inject liquid electrolytes, cycle to a certain potential, and then take this apart again, having formed whatever interfacial layer we expect to, and then rinse away the electrolyte and measure again with the same measurement system. And this is connected to the measurement system and can be done repeatedly, so we can look at the same electrode as it's cycled to different potentials, allowing us to remove many of the sample to variations you might be getting with ex situ methods. But it still doesn't allow us to look at intermediate species that might be forming. And so for that, we're also taking an operanda approach, where we have windows incorporated into cells through which we can look at the solid electrolyte interface directly. And we'll hear a bit more about that in a moment from Josh. And finally, we're also taking a cryogenic approach, where using these operando cells, we can take them to a certain state, then cryogenically freeze them under potential, and then etch through the window and into the battery itself, so that we can get much deeper down and look at these buried layers and get depth profiles throughout them. So with that, I'm going to pass over to Zoe, who's going to talk to us more about the in situ capabilities.
Hi, I'm Zoe, and I'm a Faraday Institution Research Fellow based at the University of Manchester. At Manchester, we're developing a platform which will allow us to conduct investigations into interfacial battery chemistry in situ, specifically allowing us to see the behaviour of the SEI at various stages of charge. This means we can observe interfacial phenomena without trace contaminants from a glove box atmosphere altering the surface chemistry seen in so-called post-mortem studies. The idea is to load individual battery components, i.e. cathode, anode and electrolyte, either solid or separator soaked with liquid electrolyte, that we can assemble, cycle and disassemble all inside a self-contained unit. So the in-situ platform we're developing consists of two main parts, the chamber and the platform itself. I'll talk through some of the main features of the chamber first, and then I'll talk through the main features of the in-situ platform. The chamber is comprised of stainless steel subchambers all bolted together. The stainless steel housing is capable of sealing an inert atmosphere, both argon gas at glove box level overpressures and the extremely low pressures required by the techniques we're using to characterize our battery components. The chamber can be thought as being split at the gate valve, which is here. So above the gate valve is the transfer cross, where our electrodes and electrolyte will be transferred between the in-situ chamber and the kit we're using to characterize our samples. And below the gate valve is where the battery cycling will take place under an argon gas atmosphere to ensure suitable comparison with real coin cells. The connections to vacuum pumps allow the argon gas to be pumped away, and at a suitably low pressure, the sample can be transferred to the kit without needing to use a separate vessel to do so. The clamping mechanism here at the bottom is a key aspect of the in-situ platform, which I'll talk about further in a later slide. Inside the in-situ chamber is where the in-situ platform resides. So this is the business end of the in-situ side of the project. The battery components will be prepared on specialist plates which sit inside the plate mounts. The electrode plates at the top and bottom consist of a top hat of the same current collector material as the anode and cathode. The electrolyte plate, which sits in the middle here, consists of an insulated recess where the electrolyte sits and is held in place with an insulated washer. The specialist plates are compatible with a wide variety of characterization techniques, allowing cross-platform analysis without the need to compromise any aspect of the cell design. The clamping mechanism sandwiches these components together, mimicking the crimping of real coin cells. Furthermore, the top and bottom plate mounts are electrically connected to the electrical feed-through at the bottom of the in-situ chamber, which is here. This provides easy access for electrical connections, allowing us to perform cycling and electrochemical testing of our clamped battery components. Before transfer, the components will be unsandwiched, if that's a word, and rinsed if necessary to remove electrolyte. After characterization, they'll be transferred back into the in-situ chamber, reassembled with the electrolyte reapplied, and cycled further, continuing the process without breaking atmosphere.
I'm Josh Gibson, Faraday Institution Research Fellow, based in Oxford, looking into the design, fabrication and operation of the operando cells. I'll cover this more in my talk in the Cross-Cutting Themes 4 session on the 26th of November, if this is something you'd like to find out more about. Operando studies have huge potential to advance battery research, as they allow continuous measurement of the electrode-electrolyte interface during cycling of the cell. Such experiments, utilising surface science, ultra-high vacuum techniques, are difficult to perform due to the buried nature of the interface that we're trying to study. The use of solid electrolytes with lithium metal anodes is thought to provide cells with higher energy densities. However, there is a requirement to understand how the solid electrolyte interface reacts with the lithium metal during contact and then during subsequent cycling. As a result, we've designed this solid electrolyte cell that can be seen in this animation, where we sandwich a solid electrolyte between a top and bottom electrochemical plate. These plates are compatible with many instrumental facilities, such as the HAXPES, the Royce Institute in Manchester, and with Diamond IO9 Beamline, who are actually designing this electrochemical plate. There are some Macor ceramics that can be seen to provide electrical insulation between the bottom and top electrochemical plates, whilst also being thermally stable up to high temperatures, so that we can anneal the solid electrolyte pellet to clean it. The photographs here show the top and bottom view of a prototype cell, which doesn't yet have the electrochemical connections on it that would sit around the back here. We have the ability to generate thin electrode layers on both sides of our solid electrolyte, on the top and on the bottom, allowing them to be probed with the X-rays within our studies at synchrotron sources. The assembly of this cell will occur within the glove box environment, and this is to ensure that there's a minimization of the surface and contamination on the solid electrolyte prior to loading it into our vacuum system and annealing it before depositing the lithium. Using our custom designed ultra-high vacuum chamber, which we have a lithium evaporator in, we can evaporate from our lithium crucible onto our cooled surface using a liquid nitrogen cooled stage to control the wetting of the lithium film. A uniform lithium film will be deposited on the surface with a tunable layer thickness depending on the deposition time and the power being used to heat the tungsten crucible. A mask will be used to define an area on the sample that will ensure that the solid electrolyte pellet is covered, but the electrical and chemical contacts do not short out. This layer of lithium will then be probed with X-rays to monitor the photoelectrons that come out and to identify the chemical changes that have occurred from evaporating a lithium layer on the surface. We can then continue to monitor the changes of the chemical species as we cycle the cell. By cycling the electrode, real-time monitoring of the chemical species at the electrode-electrolyte interface is possible. This includes detection of reactive intermediates involved in the SEI formation that would otherwise not be observed through ex situ studies. The same principle can be applied to any solid electrolyte with an electrode on the surface, provided that we can get a thin electrode layer on that electrolyte.
As well as solid electrolyte operando cells, we're also developing liquid electrolyte cells sealed with 100 nanometer thick silicon nitride windows. And through these, we've already been able to observe liquid electrolytes where we can see the oxygen K-edge and fluorine K-edge and detect PF6 species. So as the project really comes to fruition over the coming months, we're hoping to make these capabilities available to the Faraday Institution and wider battery research community. We're already interacting closely with both the Degradation Project and the Solbat projects in order to do this, as well as national facilities such as the Henry Royce Institute, Harwell XPS and Diamond, and new experimental capabilities coming online at the University of Southampton. And further to this, we also have a new PhD project with Jonathan Matthew, which will hopefully continue some of the research using these techniques into the future. Thank you for your time, and we look forward to any questions you may have.